and this, and this. All right. So guys, let's make sure we've got everything we need. And we're going to give you a little disclaimer for the day, and we're going to get started. So guys, you've got note-taking materials. The topic for your notes today is the mole. The date today is the 13th. Then guys, you've also got periodic tables free and ready to go. And you've got your calculators, and you've got the green sheet that I just pulled together for you. You guys good? You okay? Okay. So guys, here's where we are. And I tell you this, one, because in a few minutes you're going to think I'm no longer trustworthy. But guys, the other reason is because I don't want you to miss this. So guys, over the last couple days, we've been filling your toolbox, if you will, with some mathematical skills that we're gonna bring together today. One of those mathematical skills was dimensional analysis. It's comforting for me to know, and I don't say this accusatorily, it's comforting for me to know that actually it seems as if you guys have got a pretty good comfort level with this. We're going to apply it today in chemistry context, and I think you're going to find this good. Guys, the other thing that you've learned to do was the first homework assignment that we did when we were talking about formula masses. Refresh your memory. So guys, we were given a chemical formula or a name for which we wrote the formula, given the numbers on the periodic table. We gathered the masses of those atoms, multiplied by the numbers of them. Many times we just wrote those numbers up above the elements, and then we added them up and got the formula mass in what units? In atomic mass units. You guys good on that? Okay. So guys, with that as a background, I am now going to teach you probably the most fascinating mental construct, the most fascinating, you're going to like this. Guys, not only is this fun to learn, this is my favorite day of teaching, because there's going to be this moment. It's going to be in about 12 minutes. There's going to be this moment where you go, you've got to be kidding me. But guys, in order to get you to that moment, I'm going to lead you to a point of crisis. And I'm going to tell you right now, to bring you to this point of crisis, I am going to have to lie to you. And I'm telling you right now, I'm going to be lying to you. And the reason that I'm telling you this is because, frighteningly, you won't catch me in the lie. And then you'll never trust me again, but that's okay. But guys, I'm going to be lying to you, and we're going to be marching through this day, and we're going to be taking notes, and we're going to be learning chemistry, and all of a sudden I'm going to turn to you guys and go, guys, I'm lying to you. Here's the problem. If you don't understand the lie, you won't understand the crisis. And if you don't understand the crisis, you're going to miss out on that aha moment where we go, you've got to be kidding me. So guys, put on your CSI glasses and see if you can catch me in the lie. You won't be able to, but see if you can. So guys, here's the way this unravels. I told you already that what we need to do is we need to bring back together what you learned day one and what you learned day two. And if you've looked at the calendar, have you noticed what we're doing? Today's Tuesday, on Thursday. What are we doing on Thursday? Have any of you looked? We're going to lab. We call it a stations activity. It's a little bit different, but we're going to be in lab on Thursday. So guys, a lot of what we're going to do today is actually going to be preparation work for the lab. So with that said, this is where you need to start taking notes to make sure that you understand how to do this. So guys, we're going to go back and make sure that you're all, you don't need to write down the title, but guys, we're going to go back and make sure that you're all comfortable with calculating formula masses. So do this. Sodium chloride. Guys, figure out its formula mass. Do as little work as you possibly can, but figure out the formula mass for sodium chloride. Now guys, what's the rule? How many decimal places do we take off the periodic table? 1, right? We're going to round to 1 decimal place. Be careful with chlorine. Chlorine is not 35. Be careful, but figure out its mass. Don't forget units. So guys, what we're doing right now is we're making sure that you remember what you learned the first day, formula masses. You're going to find out in a second that I chose sodium chloride because it's plentiful, it's cheap, and it's safe. But guys, when we go to lab on Thursday, we are actually going to be doing a lab with sodium chloride. And once we've all agreed on its mass, we're going to talk about the lab that we're going to do Thursday. You guys done? You should be done. Okay. So guys, this is the way that I would do this, which probably means it would be a good way for you to do this. So in order to figure out the mass, we just need to know the mass of sodium and chlorine. So we come along and we look at sodium, and its mass is 22 and a bunch of numbers that starts with a 9. Did you all, like me, round that to 23? Yeah, I think that's right. And then, guys, we look at chlorine, and that mass, I know, it's 35.45 and then some change, but what do we round that to? 35.5. And so this is 35.5, and if the clouds align, I can do this math in 58.5. Is that right? So guys, the answer to this is 58.5 atomic mass units. Now, you don't need to do this, but you may remember that this is the way that I represented this in the homework answers to show you the complete solution. But guys, I'd much rather you have written what's in red, 58.5 atomic mass units. You guys good? Okay, all right. So guys, you can stop taking notes for a second. And what I need to do is I need to explain to you the lab that we're going to do on Thursday. So let me remind you of some things. Okay, so remember the precipitation lab that we just did? Okay, so you walked into lab and you were given squirt bottles, right? And what were in those squirt bottles? Salts dissolved in water, right? So you had salts dissolved in water, you mixed them all together, and what were you looking for? Precipitates. And what are precipitates? Substances that don't dissolve in water, therefore what did they turn into? Solids. Is that all coming back? Okay. Now guys, remember the very first lab that we did this year, the salt and sand lab. Remember that one? So in the salt and sand lab, notice the similarities, we had a solution. It was salt water. And we had a solid. It was sand, right? And how did we separate the salt water from the sand? With, no, not boil it. Then you'd have the salt and the sand together. What did we do? Filtered it. Okay, let's bring those ideas together. And guys, this is the lab that we're going to do on Thursday. We're going to go into lab, and when you get into lab, you are not going to be handed a squirt bottle like we were in the precipitation lab. I'm not going to dissolve the salts in water for you. But guys, I am going to give you the solids. So when you walk into lab on Thursday, you're going to be given a small vial that contains sodium chloride, and you're going to be given a small vial that contains silver nitrate. And I picked those two salts because when they react together, they will form the precipitate silver chloride. We'll talk more about it on Thursday. But here's what you're going to do. When you go into lab on Thursday, and before you do, we'll do this later, you're going to figure out the formula mass of silver nitrate as well. And then guys, in lab groups, you're going to go into lab and you're going to weigh out salt, and then you're going to weigh out silver nitrate. And you'll know how much salt and silver nitrate to weigh out because you will have figured out their formula masses. And then you're going to go in and you're going to dissolve that much salt and that much silver nitrate in water. Then you're going to mix them together. And when you mix them together, what's it going to do? I already told you. It's going to precipitate, right? And the precipitate is going to settle to the bottom because it's more dense than water. But now, guys, we're going to collect the precipitate. How can we isolate that solid? We're actually going to do what first? We're going to filter it first, and you're going to dump it through a filter, and the water and all the other dissolved salts will go through, and the silver chloride will get trapped inside of the filter paper, and then you're going to fold the filter paper open, and there will be the silver chloride. But guys, what we're going to do is we're going to weigh the silver chloride, and then we're going to do a little bit of math. And remember, we started with this much salt, and we're going to do this math that says if I start with this much salt, then this is how much silver chloride I should get back. And when you do that math, what will that allow you to then calculate? A percent error. Do you get the idea? So guys, basically we're taking the salt and sand lab and the precipitation lab, bringing them together because we can now do formula masses, and you're going to be weighing out these amounts of salt, dissolving them in water, precipitating them, but then now rather than just going, hey, that's a precipitate, you're going to collect it and weigh it and do a percent error. Do you get the idea? Does that all make sense? Okay, because guys, I'm lying to you. Guys, if you, and it was actually funny to watch Cam and Jared back there going, I think he's lying. It was good. So guys, where was the lie? Because what I just told you to do is absolutely impossible. That lab that I just described to you is impossible for one reason. What's the reason? Go ahead. Oh no, they do precipitate. And actually, no, silver chloride's not. Look it up. Silver chloride is insoluble. Yeah, silver chloride, and we are going to do a lab like this. But guys, the way that I describe the lab is absolutely impossible, and we're about to have a crisis. Sam, you mentioned it. What's wrong?
You can't weigh them.
Sure you can. We have balances. What are you talking about, molecular level? We know it's 58.5. Because we have a number. So what's the problem? Don't question yourself. You're right. Don't let me steamroller you. You're right. We're just going for drama. What's wrong? Why is this impossible? We have balances, right? We got balances, and they're good balances. Guys, I could even bring out my $5,000 AP Chemistry analytic balances. We got balances. So why can't we weigh this? Because you did an entire homework assignment where you figured out the masses of all of these things, and you don't even know what it means. Right? So guys, let's talk about the problem. So when we, and you got to understand, the problem here is that this number is worthless to us. So let's talk about why. So guys, what is this number? That's the formula mass of sodium chloride. We got the numbers off the periodic table. We did the math. We added them up. We got a number in atomic mass units. Now, guys, let's put this in context. How much salt are we talking about when we're talking about 58.5 atomic mass units of salt? How much salt are we talking about? So, guys, let's look at salt. So, if we're playing around with salt here, we got salt, right? So, when we talk about 58.5 atomic mass units of salt, is it that much salt? Is it a crystal of salt? No. How much salt are we talking about when we say 58.5 atomic mass units of salt? Guys, we're talking about this much salt. When we talk about 58.5 atomic mass units of salt, we are talking about one molecule of salt. One atom of sodium, one atom of chlorine bonded together. And technically it's not a molecule because it's not covalently bonded, but let's call it a molecule. Guys, we're talking about one molecule of salt. So guys, you understand the problem if you spread this out over the first homework assignment, right? Guys, our periodic tables are functionally worthless to us. Think about this. Chemistry is a hands-on science, right? And so if we're going to do math, we've got to be able to verify the math in lab. And you guys spent a lot of time figuring out all these formula masses, and now all of a sudden you realize that none of these masses have any practical use to you because this is the mass, oh, it's everywhere. This is the mass of a molecule, and we can't weigh molecules, which means these numbers are worthless, right? So guys, here's what we're going to do. I want you all to grab your periodic tables, and we're all going to get up and go down to Mr. Wakefield's store and get our money back. Because as far as we're concerned, guys, these periodic tables have no value to us. Do you guys all understand the problem? So guys, now what we're going to do is fix it. We're not going to go ask Mr. Wakefield for our money back. We're going to fix the problem. So guys, I'm going to tell you right now, this is going to get a little childish. Don't allow the childishness to distract from the learning, because you're about to have a magic moment. You ready? So guys, let's make sure we all understand the problem. We can figure out formula masses, yes? But formula masses have no functional meaning to us. Why? Because they're too small. And guys, if you don't understand what we're talking about here, don't write this down. But guys, this is what we're talking about. This is an atomic mass unit. An atomic mass unit is 1.67 times 10 to the negative 24th grams. So if that's true, what is 58.5 atomic mass units in grams? Well, guys, I'll do the math. 58.5 times this, guys, that's how much salt we are telling you to weigh when you weigh out 58.5 atomic mass units of salt. Now, guys, our $5,000 balances that I have for AP, wait right there. We're not even in the ballpark. Hi, thank you. Oh, cool. So, guys, do you now understand the problem? Do you see the problem? So let's fix it. And guys, in order to fix it, we need to find a solution to the problem. And the fundamental problem is these numbers are worthless. Don't write this down. These numbers are worthless to us because they're too small. So guys, if we can't weigh, follow this thinking, if we can't weigh, and let me show you what we're saying. If we can't weigh one molecule of salt because one molecule of salt weighs this, what can we do in order to fix the problem? What do we do? But if our given amount of salt is on the order of atomic mass units, we're still stuck. You know what I'm saying? So guys, what do we do? If we can't weigh one molecule of salt because it doesn't weigh enough, what do we do? What do we do? Get more salt, right? If one doesn't weigh enough for us to be able to weigh it, all we got to do is get more. So guys, you ready? Let's talk about more because we need to introduce you to a very interesting idea. So ready? Do you understand what we're saying? That one molecule of salt isn't enough for us to weigh it because it doesn't weigh enough, so we're going to get more. So you ready? Let's talk about more. So if one doesn't weigh enough, let's get 12. Is 12 going to weigh more than 1? How many times more? 12 times more. But guys, why did I pick 12? Because 12 has a name. What do you call 12 of anything, whether it's eggs or salt molecules? It's called a dozen, right? You guys all know, and you're familiar with this idea that groups have names. 12 is called a dozen. This is nothing like weird to you. You understand that sometimes counting groups have names. So guys, 12 is a dozen. Now, will a dozen salt molecules weigh more than 1? Yeah, 12 times more. I did the math. 702 atomic mass units. That's got to be enough, right? Guys, that's this. And this is not enough. All right, so guys, let's stop screwing around here, right? 1 is too small to weigh. 12 is heavier, but not heavier enough. So what do we got to do? Get more, right? So let's stop this 12, 13, 14 business. Let's go nuts. 144. Do you guys know the name for the counting group 144? It's called a gross. The only reason I know that is because I grew up in Wyoming where bottle rockets are legal fireworks and they sell them in dozens of dozens. 12 packages of 12, that's 144. And guys, that is what is called a gross. So guys, a gross is 144. Now check this out. Will 144 weigh more than 1? Yeah, 144. Will it weigh more than 12? Yeah, 12 times more. So guys, 144, that's got to be enough, right? What's it going to weigh? Well, it weighs this. That's more. 8,424 atomic mass units, and that's still this, and this is not enough. So guys, Obviously, that was childish, but it's going somewhere. Here's what you understand. You understand that these numbers are ridiculously small. And you understand that we are comfortable with this idea that numbers of things can have names, like 12 is a dozen and 144 is a gross. So now, guys, let's actually answer the question. The question is this: how many salt molecules do we need in order to have enough that we can weigh them in lab? And it's not 1, and it's not 12, and it's not 144. How many is it? 602 septillion. Guys, this is how many salt molecules that we need in order to have enough to weigh. 602 septillion. Now, guys, check this out. Don't look away. Just like a dozen is 12 and a gross is 144, guess what? 602 septillion also has a name. It's called the mole. Now, guys, check this out. Ready? Don't look away. 12 weighed more, but not enough. 144 weighed more, but not enough. 602 septillion is going to weigh more. How much more? You ready? This much more. Do you see it? Do you see it? Let's make sure everybody sees it. Guys, what's magic about this number? It's that number. That is the beauty of this number. And Cam, your question is brilliant, and the answer is yes. Yeah, it's because Avogadro is really smart. But guys, isn't this amazing? And we'll give credit where it's due. It's a guy named Avogadro. But here's the thing that's cool about this. If you know the mass of one thing in atomic mass units, 602 septillion of those weighs exactly the same in grams. Every time. And guys, understand, this number, 602 septillion, is just a counting group. But this guy named Avogadro figured this out. And he realized that these atomic mass units, and this is like mid-1800s, he realized that these atomic mass units were so ridiculously small that we needed a way to make these numbers functional. And he went through exactly the same thought process, and he came upon this number of things that converts exactly from atomic mass units to grams. And as Cam pointed out, this always works. And you understand the significance, right? Your periodic tables are fixed. Because guys, look at all those masses on your periodic tables. These are actually not in atomic mass units. They're in grams. But if they're in grams, how much are we talking about? A mole. So guys, the idea is this. Look at carbon. Really, do that with me. Look at carbon. What is the mass of carbon? 12. 12 what? Well, it depends on how much you're talking about. If it's one atom of carbon, it's 12 what? One atom is 12 AMUs. What if it's 602 septillion carbon atoms? 12 grams. You get the idea? Now, guys, settle in. Actually, don't. Write this down, and then we're going to settle in. So, guys, this number, this mole, this number is obviously somewhat magical, but certainly important. So let's talk. What is a mole? Well, guys, a mole is a counting group, just like a dozen or a gross. You could have a mole of eggs. That would make a really big omelet. But you could have a mole of eggs. You can have a mole of anything. It's just 602 septillion. The magic of that number, 602 septillion, is it allows you to convert masses directly from atomic mass units to grams. Isn't that crazy? Thank goodness for smart people. Yeah. Cam, honestly, when you ask your question about does it always work? Hey, Jake, be careful. When you ask that question about does it always work, I almost jumped in and explained it. Because frankly, it's not as cool as it sounds. How he came up with his number initially, I could explain to you in 12 seconds. I don't want to do it because I don't know that everybody would follow, but if you'd like to sit down and talk, I'd love it. And I'm not calling you guys dumb. I'm just saying it's outside the context. Maybe at the end, let's do this. At the end of the day, let me tell everybody how it's really easy. And then he had to figure out experiments to support it. That was the cool part. But the initial proposal of the number is a simple calculator trick. I'll show you in a minute. Okay, so guys, let's then talk about the guy that came up with the number. His name is Avogadro. And because Avogadro came up with this, we call it Avogadro's number. And guys, Avogadro's number is the number of things in a mole. Now, here's the thing. Written out, and please don't do this. Guys, written out, it looks like this. I'm going to try to zoom in, understanding this is, don't write it down, because I'm going to zoom in. Whoa, what did I touch? Oh, there. I'm going to zoom into this, I hope. Oh, there we go. So guys, looking at this number, please don't write it down, but looking at this number, let me ask you a question. How many significant digits? 3. That's it. The 6, the trap 0, and the 2. It's only 3 significant digits, and it's not perfect. They figured out Avogadro's number to many, many more significant digits. This is all you need to know. The point, guys, is it's only 3 significant digits. Consequently, we just put it in scientific notation. So, guys, again, this number is read 602 septillion. 602 septillion. Here's the question. How big is 602 septillion? And I'll be honest with you guys, I started to think about this and I got a little carried away. Please don't write any of this down. But just bask in the ridiculousness of this number. Again, don't write any of this down. So guys, 602 septillion. The question is this. How big is this group? Well, guys, to figure this out, I got a little creative. So I'm going to give you 4 examples. Ready? So how big is 602 septillion? Example number 1 is this. Guys, the computer that they just gave me, and this is a pretty sexy little machine, guys, runs at about 8 billion operations a second. So that means 1/1000, that computer can count to 8 billion. Let's put that in context. How many people are on this planet? 7, 7.5, some are saying 8 billion. So in context, how long would it take my computer to count everybody on the planet? 1 second. Put that in context. My computer can count everybody on the planet in 1 second. Guys, how long would it take my computer to count to 602 septillion? And I don't ask rhetorically. How long? A day? A minute? An hour? How long? Take a guess. 5 minutes? A lifetime? Guys, you don't even have a sense of scale. You ready? 2.4 million years. Now understand that if this was a Windows machine, it would crash a long time before that and you'd never get close. But, guys, 2.4 million years at 8 billion things a second. And if you're trying to do the dimensional analysis that I did to figure this out, good for you, but stop. It's not hard. But, guys, seriously, 2.4 million years still doesn't mean anything, right? So then I decided to get a little whimsical. Ready? How big is a mole of raindrops? So guys, what about this? If you, check this out, if you have a mole of raindrops, how many do you have? Please be able to answer this question. If you have a mole of raindrops, how many? If you have a dozen raindrops, how many do you have? 12. If you have a mole of raindrops, how many do you have? 602 septillion. It's just a counting group. Don't get that wrong. But guys, if you have a mole of raindrops, how big a bucket do you need to hold a mole of raindrops? So, would it fill my sink? Would it fill this room? Would it fill this school? Now, guys, you say that flippantly, but imagine our school full of water. That's hard to imagine. Guys, how big a bucket do you need to hold a mole of raindrops? Well, ready? If your bucket has a diameter of 100 feet, a third of a football field in diameter, your bucket would go to the sun and back 200 times. That's a mole of raindrops. So guys, what about this? My son used to be heavy into airsoft until I bought him a fully automatic battery-powered airsoft gun for his birthday and went out and played airsoft with him, and he lit me up, and we don't play together anymore. But guys, airsoft pellets, right? If you have a mole of airsoft pellets, how many do you have? 602, right? It's not just atoms. 602 septillion. Guys, if you have a mole of airsoft BBs, you have 602 septillion airsoft BBs. How big of a container do you need? And let's put it in context. When this was full, this was 10,000. How big of a container do you need to contain a mole, 602 septillion airsoft pellets? How big? The school? The field house. Guys, when I did this math, frankly, I almost chose to not give this example because it was so big, I couldn't put it in context. And then I took on the challenge and I broke out a map. Ready? A Tupperware container sufficiently big to contain a mole of BBs, a mole of airsoft pellets, would be the size of Utah, 253 feet deep. So a mole of airsoft pellets would bury the state of Utah from Idaho to Arizona to Colorado to Nevada. The entire state of Utah, 253 feet deep. That's crazy. That's a lot of BBs. 602 septillion. Can we do one more? Is that okay? I find this one the most amazing. Guys, a mole of, right, 253 feet deep. So guys, let's do this. For our last example, let's bring this back to the world of chemistry. Guys, what about this? What about a mole of carbon atoms? Again, if we have 12 carbon atoms, what do we call that? 12 is a dozen. So if we have a mole, how many do we have? 602 septillion. Guys, how big is that gonna be? Well, guess what? Guys, a mole of carbon atoms is actually this big. How many carbon atoms are inside here? 602 septillion. If these carbon atoms were the size of BBs, they would expand to bury the state of Utah 253 feet deep. You getting a sense of how small atoms are? So guys, how did I know that this is 602 septillion carbon atoms? Well, I didn't count them because that would take me 2.4 million years at 8 billion a second. So how do I know that this is 602 septillion carbon atoms? Because it weighs 12 grams. Remember how I asked you that earlier on purpose? And I love that some of you made that connection. Guys, that's the whole point. Those masses on the periodic table are grams per mole. So if I want a mole of carbon atoms, which is always 602 septillion, all I had to do was weigh 12 grams of carbon, and this is a mole, and now I know there's 602 septillion atoms in here. Do you get the idea? Isn't that crazy? Would you guys write that down with me then? So guys, this is what we now know. One carbon atom weighs 12 AMUs. Are you guys all settled with that? One carbon atom weighs 12 AMUs. Guys, we're about to transition from the concepts to the math, but you're going to find this transition smooth if you follow along. One carbon atom weighs 12 AMUs. And because that's true, this is also true. 602 septillion carbon atoms, again, as represented inside my flask, 602 septillion carbon atoms, we call a mole, just like 12 is a dozen. Don't screw that up. but we know the mass. It's 12 grams. And that's the magic of this number, Avogadro's number. So guys, let's pause and let's make sure that we can all say with confidence that what you just wrote down in blue, you can agree with. That 602 septillion carbon atoms is a mole. 602 septillion anything is a mole, but that weighs 12 grams. Are y'all feeling comfortable with that idea? Because guys, what about this then? Let's take this in a different direction. If this is true of 1 mole of carbon, guys, what about this? This is 2 moles. Write this down with me. This is 2 moles of carbon. Two moles of carbon right here. So guys, tell me this. What does this weigh? Wow, hold on. How did you get 24? Yeah, because if 1 mole weighs 12 grams, won't 2 moles weigh twice as much? Can you write that down with me? That this is going to weigh 24 grams because it's 12 times 2? Now guys, talk to me about this, and you may want to draw this in with me. Where did that number 12 come from? Why did we multiply 12 times 2? What is that number 12? It's the formula mass of carbon. It's this number, right? If 1 mole weighs 12 grams, that's the mass of carbon off the periodic table. If we want to know 2 moles, we just multiply that by 2. Now guys, what about this? How many carbon atoms are inside here? Is it still 602 septillion? What is it? That times 2, right? If you have 2 dozen eggs, how many do you have? 24. How'd you get 24? 12 times 2, because 12 isn't a dozen. Guys, the same logic works. If you've got 2 moles, and if you know that there's 602 septillion in 1 mole, doesn't it make sense that 2 moles would have twice as many? It's a little intimidating though, right? Because it's in scientific notation, but it doesn't matter. We can take that number and multiply it by 2. Write it down with me. Guys, don't be afraid of numbers. Grasp the logic. If I ask you how many eggs was in 2 dozens, you guys could all come up with 24. It's the same concept on a bigger scale with uglier numbers, but it's the same concept. So, guys, guess what? If you are now in the process of writing down everything that's on that bottom blue line, you just did all of the dimensional analysis that we're going to do for the entire year. That's it. What is dimensional analysis? Well, guys, dimensional analysis is the process of doing unit conversions. Join me at the board. Guys, you just got done doing unit conversions. You took moles and you converted it into grams. And you took moles and you converted it into atoms. Guys, that's all we're going to do for the rest of the unit. It's just that we're going to do it in a dimensional analysis grid rather than do it freehand on the board, because dimensional analysis will allow us to always do the process right. So guys, this is where I need you to answer a question, and then we're going to move forward. So guys, tell me about this. How did we get this number 12.04 times 10 to the 23rd? Well, we multiplied 6.02 times 10 to the 23rd times 2. Where did this number come from? It's the number of things in a mole. So guys, we have now identified our conversion factors. This is one of our conversion factors, the formula mass. This is our other conversion factor, Avogadro's number. So guys, what I'd like to do is this. I'd like to give you a way to organize those thoughts. Grab your green sheet. Here we go. Moles in the middle. Moles are always in the middle. So guys, what can we convert moles to? Well, we're going to start on the left. One of the things that we can convert moles into is particles. So what are particles? Well, these include atoms, molecules, and formula units. So guys, what's the conversion? Avogadro's number. Oh, wait. Oh, this is animated wrong. Guys, the other thing we can convert to is mass, and that's in grams. Sorry, the animations are wrong, but we'll make it up. So guys, how do we make the conversions? Well, if we want to convert moles to particles, we need Avogadro's number. If we want to convert moles to mass, as we identified, we need the formula mass. So guys, get your green sheet all doctored up. Use this as a reference, as we will in just a minute as we start problem solving, with the understanding that you may not use this on the test. But guys, check this out. You ready? And some of you may have already had this magic moment. Are you all caught up with me? You good? Go back up in your notes. Go back to your, don't put green sheet away, but go back to your notes. So guys, join me at the board. Atoms, moles, grams. Atoms, moles, and grams. You get it? Guys, do this with me. Watch what I'm about to do. Grab your green sheet and slide it in. What you just summarized on your green sheet is the logic that you just demonstrated by multiplying by 2 because there were 2 moles. So guys, please don't get so caught up in this that you forget the simplicity of what we're actually doing. We're converting between moles and atoms. How do we do it? Well, we multiply the number of moles by Avogadro's number. We're going to go from moles to grams. How do we do it? Well, we multiply the formula mass by the number of moles. Understand, it won't always be multiplication, but guys, this green sheet that you have in front of you is just a representation of all this logic. Notice that Avogadro's number is our conversion between particles and moles, and the formula mass is our conversion between grams and moles. This is just a summary of everything we just talked about. You see the connections? So let's use it. Guys, we're going to solve 2 problems together. Write this down with me. The question is this: what is the mass of 2.3 moles of NO2? So guys, did you like my free throw analogy for doing dimensional analysis? With the understanding that that actually was cutting really close for me because I do hate basketball. But anyway, remember the free throw analogy? You did 23 dimensional analysis problems. And again, we didn't care about any of the answers, did we? So why did we do so many? Because the answer is muscle memory. You step to the free throw line, you're developing a rhythm. Guys, now we're going to see if you've developed a rhythm. So we're going to solve this problem using dimensional analysis. So guys, when we solve problems doing dimensional analysis, what's the first thing we need? A goal. If you don't know that answer, you haven't practiced enough to have developed muscle memory. Guys, the first thing that we need is a goal. And now you're going, wait a minute, this doesn't have anything to do with Brian's weight or how old I am or in seconds. And I'm not even sure I know what a mole is. It doesn't matter. You can read. It says this: what is the mass? What's our goal? Mass in grams. So we're going to go all the way to the right-hand side, and we're going to write down grams. But guys, write down grams of NO2. Ignore me at your own peril. Because guys, very soon you're not going to be able to solve these problems if you don't identify not just grams, but grams of what. So now guys, step number 2. We need a starting point. It's the only information we're given. 2.3 moles. You guys ready for the saddest abbreviation in the world? So here, about here, 2.3 moles. That is actually the accepted abbreviation for moles. Drop the E. I know. It hardly seems worth it. NO2. Step 3, draw a line. Okay, guys, we have now set up the problem. Now it's time to take the things that we just learned and apply them. Guys, join me at the board. Ready? Join me up here. Here we go. Where are we starting? Oh, I'm going to draw another line. So, guys, where are we starting? Moles. Where are we going? Grams, where are we starting? Moles, where are we going? Where are we starting? Moles, where are we going? Grams. Now, guys, don't look away. Where are we starting? We are starting in moles. This is your green sheet. We're starting in moles. Where do we want to go? Grams, that's over here. So we want to go from moles to grams. So what do we need to know? The formula mass. So now let's go back to our problem and let's bring those things to bear on this problem. If we're going from moles to grams, we need to know the formula mass. Didn't you do an entire homework assignment on figuring out formula mass? Yes. So guys, we need to change one thing, however. Check this out. Do this with me, but be careful. Don't get ahead of me. What is the mass of nitrogen? Look it up. 14, right? But what number are we going to take off the periodic table? What did you learn in assignment 1? 1 decimal place, right? Are you all gathered on that idea? Not anymore. Here's the rule. How many decimal places do you take off the periodic table? The answer is this: never less than 1 and more if necessary. Never less than 1, more if necessary. So what I want to do with you right now is never less than 1. The next problem we'll talk about more if necessary. But here's the deal. There is no longer a universal rule that says 1 decimal place. The rule is actually this: never less than 1, more if necessary. So guys, right now we're just going to take 1, and you'll understand why on the next problem. So the mass of nitrogen is 14.0. What is the mass of oxygen? 16.0 times 2, 32.0. Now guys, we add those up and I get 46.0. Please don't write this down, but check this out. That means 46.0 grams of NO2 is equal to 1 mole of NO2. That's what we just figured out. Now let's bring our dimensional analysis skills to bear on this. Guys, what goes on the bottom, the 1 mole or the 46 grams? The 1 mole, because it's got to cancel top to bottom, right? So we're going to go like this. 1 mole of NO2 is 46.0 grams of NO2. Is that true? Yeah. 1 mole is 46 grams. Now guys, look at what happens. Our moles cancel, we're left with grams. Are we done? How do you know? Because this is the same as that. So now all we have to do is the math, and we go 2.3 times 46. And guys, I'm going to switch colors so it stands out, and I'm just going to write it here. I get 105.8 grams. But that's not the answer. Let's do significant digits. How many do we get here? 2. What about there? 3. These are not perfect. 3. And the 1 doesn't matter. So 2 and 3. So how many do we get in our answer? 2. So that would be 110 grams of NO2. You guys okay? Questions? Yeah. Because I took 2.3 times 46 and then didn't divide by 1 because it doesn't change anything. Just doing the math. What else, y'all? You guys good? Okay, let's do one more.
I'll give you a second to write it down.
So guys, it says, how many molecules of water are contained in 25 grams of water? So allow me, if you would, to put this in context. And you obviously saw me get this, so I didn't weigh this. But I know the density of water is 1 gram per milliliter. So this is 25 milliliters of water. It weighs approximately 25 grams. So guys, the question that we're asking ourselves is this. How many water molecules are in here? How many water molecules are in here? You understand the question? Let's go figure it out. So guys, I want you to do the first 3 steps on your own. Don't go on, but do the first 3 steps. If you don't know what those are, you haven't developed a rhythm. Set a goal, pick a starting point, and then my tough step, draw a line. Although first line was not bad. Let's look at it again, shall we? Not bad. Had a little hiccup at the end, but I'm okay with it. Pick a goal, pick a starting point. But guys, don't get ahead of me. There's all sorts of pitfalls in this that are going to cause you problems. Let's do this together so we can do it right. Okay, so let's do the first 3 steps together. What is our goal? Molecules of water. And guys, you can simply represent that like this. Waters. You don't need to write out. You can write out molecules if it's helpful, but it's just waters. How many waters are there? Well, what's our starting point then? 25 grams. And then a line. So guys, let's stop for a second and let's make sure that you didn't write down 25 grams of water. It's 25.0 grams of water. Why do we care? That zero's significant. Okay, so now guys, let's play the same game. Where are we starting? Mass. Where are we going? Molecules, which are what? So guys, here we go. Mass to particles. We're going to go mass to particles. So if we are going to go mass, if we are going to go mass, stop it. If we're going to go mass to Y. Oh, I got ahead. Oh, look at that. Never mind. If we're going to go mass to particles, guys, mass is over here. Where's particles? All the way over there. So how on earth are we going to go from mass to particles? We're going to go to moles first. So our process is going to be mass to moles and moles to particles. Mass to moles is going to be the formula mass. Then moles to particles is going to be Avogadro's number. So this is going to take 2 steps. Ready? Let's do it together. So guys, it goes like this. We're going to go mass to moles and then moles to particles. So guys, what's our conversion from mass to moles? Formula mass. Guys, watch. Watch, watch, watch. Ready? What is the mass of hydrogen? 1.0. Guys, please do not write this down, but watch. This is important. The mass of hydrogen is 1.0. Now guys, check this out. How many significant digits are in 1.0? 2. How many significant digits are in 25.0? 3. That's bad. Let's talk. How many decimal places do you take in your masses? In the first problem, the answer was never less than 1 decimal place. But there was this additional idea, or more if necessary. Guys, watch. When is it necessary to take more? And the answer is this. The other rule is your masses never limit significant digits. Let me say that again. Your masses never limit significant digits. So if you've got 3 significant digits here, you've got to have 3 significant digits in your masses. That requires more decimal places. So guys, go to hydrogen on your periodic table and give it to me to 3 significant digits. It's not just 1.0. What is it? 1.01. But there are 2 of them. So it's not 1.01, it's 2.02. Now we need oxygen to 3 significant digits. What is it? 16.0. Now guys, we've got to add these up. And it adds up to 18.02. So now guys, think. 18.02 grams of water is 1 mole. What goes on the bottom, the grams or the moles? Grams, so do it with me. 18.02 grams of water is 1 mole of water. And grams cancel. Are we done? We're not done. How do we know we're not done? Because we're in moles, and we want to be in molecules, and those aren't the same. So now, how do we get from moles to particles? Avogadro's number. And guys, be careful with divide by, multiply by. We don't do math. We just need the conversion. Dimensional analysis will figure out the math. So guys, how do we get from moles to particles? Look at your green sheet. How do you get from moles to particles? Avogadro's number. Now, Avogadro's number says this. Watch my hands. 602 septillion is 1 mole. That's true. 602 septillion is 1 mole. Which one goes on the bottom, the 602 septillion or the 1 mole? The 1 mole. So guys, 1 mole of water is 602 septillion water molecules. Now moles cancel, and now we're done. This is where we grab our calculators. And we go 25 divided by 18.2 times 6.02 times 10 to the 23rd. And now, guys, let's get significant digits. We've got 3, we've got 4, and yes, Avogadro's number is only 3. So we get 3 significant digits. So I get 8.35 times 10 to the 23rd water molecules. Now guys, as you're doing this math, if you do not remember that to put scientific notation in your calculator, you use the EE button, you need to work on that. So guys, there you have it. We started with a crisis. We learned something really interesting about the mole. And now we've engaged in some math, guys, that, let's just call it what it is. It's going to be hard. So guys, here's the deal. Same offer that I made before. You're going to go home. You're going to work on these tonight. And then when you need help, you're going to come and get help. But guys, listen carefully. Set a goal. Starting point. Draw a line. Reference your green sheet. Label your numbers. Do this on another sheet paper. Put your stinking phone away. I don't mean that but I mean when you're home doing homework, get your phone. Guys, let's just we're all at right. If you mean put your phone away by slide corner of your desk, it's going to be back quickly. Give it to your little brother or sister and let them run away with it. Get your phone out of your room and focus for 30 minutes. So guys, let's look at the homework assignment. It's assignment number 3. It's long. Look on the back. Stop at number 22. 23 on, we've actually written out of the curriculum for the next few days. We're never going to come back and solve these problems. Just a moment. So don't do beyond number 23. Guys, in addition to that, on Thursday we are going to lab, but we're not doing a lab. You're going to have an additional set of practice problems to work on. Guys, do these problems at home. Come get help if you need. If you're doing remediation, it's today and tomorrow. Have a lovely day.